that was my question, was what does it depend on? So I'm not asking for a z-score. I'm just saying in a problem, what would tell you which z-score to use? So there's this guy. And we've used this formula before. And I just want you to see how it's just that formula kind of grown up a little bit, right? Yeah. So if I don't know mu, I take a sample and I use x bar instead. So what is x bar? Sample mean. If I told you the average age of gross fund students is 25, you with me? And then I go take a sample and we calculate an average age of 27. Which one of those is more correct? The 25 or the 27? 25, that's the population mean. So when do we use x bar? We use it when we don't know mu. X bar is kind of like an approximation for mu. Is that good?
Yeah.
Y'all with? So that's one thing this tries to do, is it tries to improve upon x bar just being an approximation. So the give or take there is to kind of like expand it a bit to give a more detailed explanation to somebody else. We're not really too sure about this, right? Same thing with standard deviation. When would I use S if I don't know sigma, right? Because the sample standard deviation is an approximation for the population standard deviation. Are you guys cool with just that? Just that? Okay. All right. So one question that we were talking about right before class started, Charlton, help me remember exactly what were we talking about?
Number 21 and number 22 on the homework.
And not that one. There was something else.
Oh.
That one I don't. Okay. In the homework, 21 and 22, both talk about mathematically what would have to happen here. If I increase n, and I want this piece to stay the same, well, if I just increase n, will this become bigger or smaller, this piece? If I make n go up, will this piece get bigger or smaller?
Smaller.
Because I'm dividing by more, correct? What would I have to do to z to make this stay the same as it was? Go get bigger. Does that make sense? So fundamentally, that's what those problems are talking about, just looking at the equation. If you made this part go up, what has to happen to keep this piece the same? Z's got to go up. Okay, let me stop for a minute. Okay. So for a given sample size, if I want to increase my confidence, I increase the size of the interval. Why does that make sense? Because then I'm catching more data. Is that cool? So if I create a 95% confidence interval, the fundamental idea is if I catch 95% of the data, I'm going to be 95% confident that I caught a specific thing. That's the idea. How we doing? Okay, everybody's averting their eyes. So help me out. Where am I losing you? Let me see. Okay. So I know that in a normal distribution, if I go a certain number of steps up and down, so for example, if I go 1.96 steps down, 1.96 steps up, I'm going to catch 95% of data. We know that, right? Mm-hmm. So if I have a normal distribution and I go up and down 1.96 steps, how certain am I that I caught a specific data point? 95% certain. Let me call it confident, right? I'm 95% confident that I caught a specific data point. Any specific data point, correct? I'm 95% confident I caught anything. So how confident am I that I caught the real mean? 95% confident. That's what a confidence interval is all about. So if I want to be more confident, I just go out further. I just catch more, right? If I wanna be 95% confident that I catch a certain kind of fish in a lake, I catch 95% of the fish, if I can, you with me? Then I would be 95% confident that I caught a specific fish. Does that make sense? Like a fish swallowed my wedding ring. I was gonna propose and it went in and I saw the fish, so I'm like, damn it! So for some reason, I just wanna be 95% confident I catch it, so I catch 95% of the fish. Then I am 95% confident I caught that fish. Is everybody with that? So almost everything we talk about has a physical analog. We can actually think of it in the physical world. That's what a confidence interval is, catching so much data, and therefore I am that confident that I caught something specific. Now, what is it that I'm trying to catch? The real mean. So I'm that confident I caught the real mean because I'm that confident that I caught any specific data point. Can we stop for a minute? Yes.
So half of the confidence interval, you would call that the error?
To construct the confidence interval, I have the amount that I have to go up and down by, and that's the error.
The error, okay.
Mhm.
Cause I think in the book, they call it the CE or something like that. That's confusing, they call it something else.
They call it the EBM.
Oh, BBM.
Yeah, sounds like some kind of weird missile. Error bound maximum, right?
Right.
So we just call it the error. Yeah. Okay. All right. I like that. Okay. All right.
When it says like what distribution would you use, is that when you do that M squiggly line?
So for section 8.1, we're going to be using the normal distribution, right?
Oh, so it's just.
And
M.
that's only if it actually is normal.
Okay.
So either it's going to say it's normal. If it doesn't say it's normal, what's got to be true?
Has to be above 30.
Sample size got to be more than 30. I like it.
30 is not big enough.
30 itself is officially not big enough. Yeah.
Okay.
Yeah. Okay. All right. Okay. So, chapter 8 builds on stuff we've done before. It's just kind of like the next step. All right. Let's see.
But what we were talking was the difference between the sigma X bar
Yes.
and F.
Yes.
Now those are different concepts.
Yes. So, I'll say this. When we get to section 8.2, that's going to become much more important. And that's where I'm going to talk about that.
Is that today?
That's today, yeah. Okay. So, just to kind of remind everybody, we have so far developed this formula here. Right? And what that does is it takes an estimate of the real mean and it kind of improves upon it.
Yeah.
So, going way back, if I started working at a company and they said, yeah, the mean income of employees is $45,000, right? That doesn't really communicate to me how much I could really expect to make. So if they give me a range, kind of make a confidence interval, 95% of the employees make from this to this. Wouldn't that be more informative? So if 95% of the employees make from 44,000 to 46,000, okay. If 95% of the employees make from 40,000 to 60,000, okay, that kind of helps me figure out, oh, I have more chance to, if I excel, I have a higher chance to get more income, when this one seems to be keeping it closer to the mean. Okay. All right. Okay, so this guy we created last time, this one, and then of course we just took a minute and we figured out this formula for how big of a sample do I need to make the error be within something. Okay, so let's do this. So last time we did that one side of that sheet. Let's do another example real quick, and then I gotta talk about the percentages. So let's do this. We know population standard deviation is 1.2.
quick little bare bones kind of example. Yeah.
If you don't know N, Professor, how could you know what E is?
If you don't, what? Oh. All right, we'll do that. We'll do that as part of this. Right, so I'm gonna do an example that uses this and this. So right now, if I don't know E, how do I know N? Well, that's a silly question because I calculate E based on N, correct? Same thing here. If I know E and I don't know N, I can calculate N based on E. So, here we go. Has everybody got this here? Okay. All right, my creativity is tapped out today, so it's just items. That's all there is to it. So can you just take a minute and identify what we know? What do we know here? What's the 11.2? What symbol do I get that? Sigma. Of course, 48
N,
and 5.1
X bar.
X bar. So now if I say create the 90% confidence interval for the true mean. Okay. So this is what I mean, most problems, and why do I say most? Because once we get to section 8.2, we're gonna be using the 1var stats in our calculator to calculate our own stuff. But in section 8.1, they're gonna give you everything except the z-score. So they did not give me the z-score, but how do I get the z-score?
Plus minus 1.645
Yeah, well, let's back up a second. How do I get it?
on that paper.
How do I get it? What process do I go through? How confident do I want to be? 90%. Can you draw that? Take a second. Draw it. All right. All right, so what am I missing here? What's this?
0.9,
0.9?
0.05.
Okay. So there's 90% inside, 10% outside, 5% on that side, right? Or either side. Okay. So this will be 0.05. So what I normally do, I need both of these z-scores, but not really, because they both have the same number, just one's negative, one's positive. Is that cool? Because of the symmetry, is that right?
Yep.
Okay. So I could look up 0.05, I just normally do that because that's a quick one. Or I could look up 0.95 because that's the area below this. So basically, why can't I just look up 0.9? Why can't I just look up 0.9 in the z-score? It only understands the area below a z-score. 0.9 is between two z-scores, right? Between two firms. So it's not the right area. The z-score chart won't give me the right number because it's not the right area. So I need the area below either one of the z-scores I want.
Yeah.
So if you look up 0.05 in the body, don't say anything, just look it up, and I'll give you a moment, and then I'll remind you about a shortcut if you forgot about it. So when you look up 0.05, obviously on the negative side, right?
Yeah.
How do I say obviously? Because I'm below the mean there, right? Now tell me, what do you guys get? Yeah, you get negative 1.645. So what's that one automatically have to be? And how do I cut it? What's the area below this z-score? 95%. So if you look at 0.95 on the positive side, you'll also get 1.645. So I don't have to find both of them. When I have one of them, the other one's the positive of that, right?
Yeah.
Okay, or just the opposite sign. Now you see why in the formula there's a plus or minus, right? Or not now, we saw that before, but just to remind you guys, why is there a plus or minus? Because they gotta go up and down. Positive z, negative z, right? Okay, I like it. Okay, so
Now I just plug and chug. Right? Again, they're gonna give me almost everything. Normally, the only thing I have to calculate is the z-score. So now I just plug stuff in. So I got 5.1, give or take, 1.645 of these. And by the way, real quick, I forgot to ask this. Why is this normal? Does it say it's normal?
Samples over.
No,
Yeah, n is greater than 30, check, right? Okay. Otherwise, I wouldn't be able to do this, right? And now it's just plug it in the old calculator, right? So again, it's built off of, if I go up and down a certain distance, I catch a certain amount of data. And then I'm that confident that I caught a certain data point, right? If I catch 95% of the people in a city, this big evil guy going around my net and catch 95% of the people in the city, how confident am I that I caught Tim, the guy that owes me money? How confident am I? 95% confident, because I caught 95% of the people. So what I highly recommend is you do the error part first. 2.66, okay. And then I do 5.1 minus that, 5.1 plus that. Is that,
How do you know how much to round?
so here's the thing, so make sure your error is one more decimal place than this guy.
Oh. Okay,
That's a good rule of thumb.
cool.
Okay. So it's 5.1 minus 2.66.
2.44.
Hmm?
2.44.
2.44, and then plus. All right, so now, how you guys, so there's always a conceptual part. And I really don't want this concept to be, it's, we already know if we go up and down a certain amount, we catch a certain amount. And if I catch a certain amount, that's how confident I am that I caught any specific thing. That's how this is built. What that translates into, nuts and bolts wise, is a very, very plug and chug situation. The only thing I normally have to calculate is the z-score based on how confident they want me to be. Now, how do I interpret this? Yeah, we are 90% confident that
Interval.
the interval 2.44. Normally I would give units, but I didn't. So make sure you put the units here if there are some. Contains what?
The real.
Yeah, the real, the true, the population. I normally say true. Contains the true mean. So again, in the background of this, there is a true mean. We took a sample and we got a sample mean. I would put money that they're different, because every sample is going to have some natural variation in it, right? It's going to overall be less or overall be more. That's just the way samples work. But if I go up and down 1.645 steps, right? Then I have a 90% chance that that's going to catch that mean. If some other group came along and did another one, they might not catch the mean. And so if I had a bunch of groups, a bunch of different research groups collecting data from the same population, what percentage of theirs would not catch the real mean? 10%. That's why mine has a 90% chance. Yes?
What do you call 1.645? Sigma X bar?
No. Okay. What is 1.645? It is the z-score.
I mean, the 1.617.
1.617.
The 11.2 over square root of 48.
Oh, yeah, this is sigma x bar, of course,
Okay,
yeah.
okay, thank you.
Which just means the standard deviation of the sample means.
Can you confident
And later I'm
level,
gonna ask you how.
can you confident interval be negative?
Oh, sure, yeah. Can the mean of something be negative? I know we're in California, but are there parts of the world where the temperature gets negative?
Yeah.
I love it, somebody's saying no. So, yes, they can get negative, right? So if I made a confidence interval for the true mean temperature Fahrenheit in Antarctica, that whole thing would probably be in the negative. Yes? So you could, yeah, if the data can be negative, the confidence interval can be negative. Hell yeah. Okay. All right.
Later you're gonna talk about how the sigma x bar is different than the s.
Yep. Section A2 is all about what do we do if we don't know sigma. So then we're gonna focus more on S. Yeah. Okay. All right. So I promised to do this. Now, real quick, guys, can you guys tell me if I have a sample size of 48 in this, what error does that lead to? What was the error here? What's the error? 2.66. So when the sample size is 48, it leads to an error of 2.66. You guys with me? Just because that's the math, that's how it worked out. If I want the error, so now I say, same problem, but now we want the error. We're like, no, that's too much. We want the error to be 1. We're like, 2.66 is too much, right? The boss comes over and says, no, make it 1. Oh, shit, okay. How large of a sample will that take? So a sample size of 48 gives me an error of 2.66. In order for me to push that error down, meaning I want to be more certain in the first place about the information I get from my sample. Should my sample size get bigger or smaller?
Bigger?
Yeah, if I want to be more certain about what I see in a sample, it has to be a bigger sample. We know, you guys knew that from day one. You know a bigger sample's better. And always in the background of all of this, it's truly random, right? I don't care how big you make a convenient sample, it's gonna suck. Okay. What variable is the question asking us to solve for? N. So I never would teach like this, but now that you've suffered through my attempts at explaining the concept, when you look at the question, you're like, okay, it's asking for N, find a formula that's solved for N. Does that make sense?
Yeah.
So the only one we know so far is this one. And do we have everything we need for this formula? So this is still that same situation. So I know the z-score. I know the standard deviation. Where'd it go? 11.2. And I know the error I want. 1. Right?
Where did you get the error from? Oh, it gives it to you, okay.
5 times 300. I think something like 300. I don't know. Try to do my head, you never know.
$52.18, 19?
Oh, did you square it?
Probably did.
Oh, I could have just totally did it wrong in my head. What is it?
52.19.
No, yeah, I think, I don't know what happened over there.
339.
This by itself would be 120 something.
Oh, I looked up the one.
This is 339.44.
Yeah, I agree with that. So then you would round it up to 340. You always round that number. If it's decimal, you always round it up. So what does that mean? What does that 340 mean?
That's the same. That's the population.
That's the sample size I need to make the error 1. How big of a sample did it take to make the error 2.66? 48. So if I put 2.66 right there, my answer would come out around 48. I already know that. I already know a sample size of 48 gives me an error of 2.66. Do you guys see that? I already know that. I want the error to be 1 now. So of course my sample is going to have to be bigger to make the error better, right? So that makes sense. It's way bigger than it was. Okay, maybe. Yes?
Which is the other one that you have to round up only n? Is n the only one you have to round up?
This we round up because I really want this to make sense. You have to have at least this much. If I did 400, I would be even better than 1, wouldn't I? Right? I would have an even better error than 1, so I'd be within 1. I don't want to go any below this. So I would never round this down because that's automatically wrong because it's got to be at least this. That's why you always round this up. Yeah.
Is there a name for that idea?
No.
Like
Because
how-
again, you cannot generalize that. In this instance, it doesn't make sense to ever round down. So that's why we round up. There's
'cause it's
nothing.
like the same concept like when you get P50 or something like that, right?
Oh,
You have to
sort
round
of,
up
yeah.
So it covers it.
yeah, because it's got to be at least that. Yes, we round up because you can't round down because then you wouldn't be at least that. Yeah.
Okay.
Okay. Okay. Anybody else? Oh yeah, need this handout from last time, the one that's got dolphins on one side. Doesn't have pictures of dolphins. Sorry, just talks about dolphins. Okay. You already got it. Yeah. Yeah. All right, guys. So you just have to get into that homework to see how you feel about this. You have to try a few of these problems out to see if it kind of flows. Okay. So last time we did this side with the dolphins. Right? So what I want to work towards now, and there's an example of the end thing we did last time. Okay. So if you weren't here last time, you can watch that video if you want to. You can ask me questions, that's fine. So I want to be able to do this side today. And I kind of hinted at what we're going to talk about partially. So I'm going to try to move us in this direction.
And you put this handout on Canvas too, right?
I think so. I could. Anytime, so Canvas is not an automatic consideration for me because I'm not an online teacher. I don't want to ever be an online teacher ever again. Dear God, no. So I don't automatically think about Canvas. So if you want some handouts up in Canvas, I think I've got several of them. I'm pretty sure I activated the chapter 7 and 8 stuff today up in Canvas. So if you look in Canvas, there's modules, and then there's one that says chapter 1 handouts, chapter 2 handouts, chapter 3 handouts, I believe. Yeah, and I think I activated the chapter 7 and 8. So this is 8, chapter 8. Okay. So, so last time, correct me if I'm wrong, we did go through the derivation of the formula, the p hat. You guys remember what p hat meant? Besides a piece of clothing I don't think I ever want to wear? Yeah, good. So P by itself is the population percentage. P hat is the sample percentage. Okay, I like it. So we actually created that formula last time. it feels just like the other formula. It's got our sample data, give or take a certain number of standard deviations. So we're gonna use this again later because it is the standard deviation for this kind of situation. You're gonna see that again. We're gonna kind of steal it from this later this semester. Okay. So, one thing we have to talk about is, how did I know in this problem that I could even do anything?
It's normal.
It's normal. Why was this normal?
The sample size is over 30.
Sample size over 30. That is the check for means. If I'm doing something related to means, the sample size has to be greater than 30 if they didn't say it was normal already. So I need a similar test if I have percentages. That same one won't work. So I'm going to show you why that same one won't work. And to help me do that, I'm going to bring back an old handout. Is it up there yet? I don't know if you guys remember this dude. So I want to talk about it just a little bit, and then I'm going to draw some other stuff. We talked about this back when we actually did this handout, and I asked you if that looks normal. I mean, does that look normal?
Yeah.
Hell yeah, that looks very normal, right? One big reason, now real quick, this was flipping a coin 14 times, and it's a fair coin. So what would the mean be if I flip a coin 14 times? How many heads would I expect to get? That's why it makes sense that the highest bar is close to 7. In this case, it's exactly 7. Are you guys with me? So why does this look normal? Can somebody tell me? Don't just say, because it looks normal. Why does it look normal? What about it? Good. It starts low. Okay, good. It starts low, goes high, goes back low, right? That is the necessary requirement for something that to at least be roughly normal, right? This is even better because it's perfectly symmetric. That's a bonus, right? We've seen stuff that we said was roughly normal and it wasn't really symmetric. This is symmetric. This is looking pretty damn good. Okay. Let me ask you this. Why was the mean 7? Because what's n? 14. And what's p if it's a fair coin? And I flip it. What's the probability of heads? 50%. Right? So half of 14 is 7. That's why the mean is that. So real quick, what if instead, let me see if I can do this here. Maybe. Paper. I just need paper. There we go. Paper. Keep it all up here so I'm not going back and forth. Okay. What if I flipped a coin that was weighted? So somebody's coin that they weighted so that they can make sure they know what the answer is going to be ahead of time, right? Mm-hmm. So the best you can do is weight it so that it's more likely to show up. So what if somebody weighted it so that the probability of heads was just 0.01? Is everybody with me? Right? If I weight a coin a certain way, when I flip it, it's going to be more likely to land on a certain side, correct? Okay. So I can weight it in such a way so that it only lands on heads 1% of the time. What if I flip it 14 times then, what is the expected number of heads? Yeah. Because if I flip it 14 times, expected number is another name for the average. The average is n times p. So if you 14 times 0.01, 0.14. So now, where will the tallest peak be? There's a 0 here, there's a 14 there. Do you guys agree there's 2 walls here? What's the least number of heads I could get if I flip it 14 times? 0. What's the most? So there's 2 walls built in, correct? If I flip it 14 times, I am not going to get 15 heads. If I do, I'm not sure what I just took. Something's wrong, right? Are you guys kind of with me? Okay. If the mean is now 0.14, where should the highest bar be now? No. The mean is 0.14. Why was the highest bar on this paper around 7? Why? Because what's the mean? 7. And what's the other name for the mean? Expected value. So that's why that's got the highest bar. I expect it to be close to the mean. Now what's the mean? What's the mean? 114. So where should the highest bar be?
Why 0?
Right next to 0, correct? So this is the highest bar now, correct? What's it gonna do from there if that's the highest bar? It can only
Down.
go down. Does that have any chance to be normal?
No.
Nope. Okay. You guys with me? Okay, so these two walls, I need the mean to be far enough away from that wall so it's got room to go up. Can you guys see that? This mean was way too close to the 0 wall. It starts high and goes low. It's got no room to go up. Does that make sense?
Yeah.
Okay. Don't I have another wall? Over here, right? So if the mean was too big, it would be slammed up against here. It would have the same problem just the other direction, right? You guys all with me? Does that visually make sense? This makes more sense to me than n greater than 30 because you can frickin' see it. I'm gonna have to have 2 requirements. I need NP to be big enough. And the funny thing is, let me ask you this. If this is the expected number of heads, wouldn't that be the expected number of tails over there? If I expect 0.14 heads, I expect 13.86 tails. Does that make sense? If I flip it 14 times and I expect on average 0.14 heads, I expect 13.86 tails. Does that make sense? If it's not one, it's the other one, correct? All right, so this would be the expected number of successes, NP. This would be the expected number of failures, NQ. So I need this to be in the middle. I need the mean and the number of successes and number of failures to be somewhere in the middle. So it's got room to go up and room to come down. So why was this one so freaking perfect, this dude? Why is that so perfect? Because the freaking mean is right in the middle. It's got the exact amount of room to go up, and then it comes perfectly back down because the mean is right in the middle, right? Now, if the mean was at 6, it would still have room to go up and come down. It wouldn't be perfectly symmetric, but it would be pretty damn close. So what does that mean, Jeff? You always do this, Jeff. You always talk all this concept. Just tell me what the shit it means for me. Okay, here's what it means. Coming back to you. If I have a percentage problem, they're trying to make me do something with a percentage. Right now, the only thing it would be construct a confidence interval. Construct a confidence interval for a percentage. For a mean, I need n greater than 30. For a percentage, I need NP and NQ both to be at least 5. And what that means visually is I'm far enough away from one wall and I'm also far enough away from the other wall so that it goes up and goes back down. Now, if you don't enjoy my conceptual explanation, you can just memorize that, right? Just like n greater than 30. The funny thing is, n greater than 30, I had to construct an alternate frickin' universe and take us all there, right? And that was some weird shit. I agree, it's weird shit, I agree, because it's a weird concept. It's not very visual. This is a beautifully visual concept. If I go back to the picture, so let's see, this is like 1, 2, 3, 4, 5. So if the highest peak was actually at 5, it would have room to go up and then room to come back down. Is that cool? So this one controls distance from that wall, this one controls distance from that wall. So they both basically just say, make the highest peak somewhere in the middle. So it's got room to go up and room to come down. That's it. That's nice. Yes?
You know, you said Q was the number of failures. Is
Yes.
it always gonna be failures?
NQ. What does Q mean again? What's
Is it-
P and Q?
Opposite of
Opposite of P, what's P? Don't say opposite of Q.
Uh,
P is the probability of success, so Q is the probability of failure. NP is the expected number of successes, NQ is the expected number of failures.
And the failures could be, doesn't matter, in the wall or always to the, on this wall.
Well, the way I've set it up, it's this wall, but I could make P really big and then it would sort of switch.
Okay.
So to be honest, these each control one side. It just doesn't have to be a specific side, it kinda depends.
Okay.
N is your number of trials, right?
Yes. So, real quick, for a mean, if I'm doing a confidence interval for means, what's gotta be true about the sample size to tell me it's normal?
Gotta be larger than.
N greater than 30. Now watch this.
What if I flipped a coin 40 times? That's bigger than 30, right? Well, let's say I've weighted this coin so well that it only shows up heads 1 out of every 1,000 times. Are you with me? So I'm getting really good at weighting these coins. What will the mean number of heads be now?
0.004.
Yeah, it'd be 0.04, right? So where will the tallest bar be again? I'm aware I keep saying Barbie, but where will the tallest bar be? Here again, right? So N is freaking 40, that's bigger than 30. So I want that to make sense. For a mean, all I need is sample bigger than 30, that's all I need. For a percentage, I have to involve the percentages in there. It takes a little bit more for them to be normally distributed. N greater than 30 is not good enough. Okay, maybe. So everything I just said boils down to, instead of N greater than 30, you check NP hat, NQ hat bigger than or equal to 5 to see if it's normal enough, right?
They have to both do it.
Both of them. Because if one of them doesn't, that means it runs too close to one of the walls, it doesn't have a chance to be normal. If I put the highest peak in the middle, now it's gonna be normal, yes? Because it goes down from there. That's exactly what I want a normal curve to do. Okay, so coming back to this, now you see what I mean when I say this. So let me get everybody back up to speed with this side of the sheet. We took a sample of 652, 459 of them voted, finding 90% confidence interval for the true proportion of people that voted. Okay, so proportion just means percentage. We did P hat last time, we didn't calculate it that I remember, but if you can say it in English, you can do it in Mathfish. So how many people voted in the sample? No, how many people voted?
652.
How many people
459.
voted? in
Oh,
this-
459.
Out of?
652.
So that's how we say it in English, that's exactly how we do it in Mathfish, right? 459 divided by 652, now tell me what that is. 0.704, I love it. So these P hat and Q hat have to be at least 3 decimal places. So if I were you, you could just make every damn thing 4 decimal places, right? Except for z-scores, because the z-score chart only goes out 2 places. Okay. Poor little dude. What's Q hat then? Yeah, so I don't care what clothing they're wearing, P plus Q is 1, right? So these guys are wearing hats, who cares? They still have to add up to be 1.
Wait, how did you get that? The 2.96?
P plus Q must be 1, no matter if they're wearing hats or not. So if P hat is 0.704, do 1 minus that to get Q
Oh.
hat, yeah. Just like before. Same thing we did with P and Q, right? What's N?
652.
Yeah. Be really careful. I always get somebody tell me, it's gotta be the biggest number, right? It's the total number of things. So what does this mean? What do I do here?
Multiple.
Now, can everybody do this real quick? What is N times P hat?
459.08.
Double check that, everybody. You never know. Charlton could have just went completely crazy. You guys get the same thing?
Yeah.
Okay, now real quick. What was the number of successes in the problem? So a little tiny shortcut. How did we calculate p hat? Didn't we do number of successes divided by n? So won't n times p hat equal the number of successes? Why is that not exactly 459? Beautiful, because we rounded p hat, so of course it's not going to be exactly, right? And again, not a big deal. Some of you guys might realize that's a shortcut because I'm going to see what NP is already, NP hat. NQ hat is just the rest.
192.992.
If I just do 652 minus 459, that's basically what this is going to be because it's the rest. Or you just multiply this shit together. What are you going to get? Sorry?
192.992.
Yeah. And both of these are what? Greater than equal to 5. What does that mean?
Normal distribution.
It's normal enough. So this check just takes the place of n greater than 30. That's all it does. And I feel pretty good that you guys are really comfortable with n greater than 30. You know that. This is just the check I have to do for percentages, right? Yeah. All right. So now, don't say anything. Take a minute. You see how confident I want to be?
Yeah.
Much more than normal. So can you guys take a minute and just figure out the z-score for that? Don't say it. He remembers how to get that. It's not going to be on your baby chart, unfortunately. Just remind you guys real quick, if you don't remember, see down here in the bottom of the positive z-scores, see you have the little baby chart? So if I ask you for one of these, hey, that's nice, right? But I asked for 96, damn you, Jeff. Who thinks they found it?
Plus minus 2.05.
Alright, so I got one vote for 2.05. Anybody else find something different?
Yeah, 1.75.
Ah, okay. So what you guys did was you looked up 0.96, right?
Yeah.
Okay. That would be finding the z-score that has 96% below it.
Yeah.
Do you see how that's different from what I want here?
Yeah.
The chart will never understand this area because it only understands areas below the z-score. So tell me, 96% inside, right? What percentage is outside? 4%, right? So what percent is on that side? 2%. So if you look up 0.02,
Wait, but I thought it's gonna be like the same number.
totally, yeah, so it doesn't matter which one of these you find. But again, if you look up 0.96 in the chart, it's gonna find the z-score that has 96% all the way below it.
Oh.
That's not what this is, right? I wanna catch the middle 96%. The z-score chart only understands areas that are below a z-score. 0.96 is not below any z-score I need. Do you guys see that? In fact, can you guys tell me what percentage is below that z-score? 0.98. Look up 0.98. Positive side, right? Look up 0.98. What do you get? Yeah, of course you get the same thing. But you come back to Javon's point that you only have to find one because it's symmetry, right? It's symmetric. So once I know one of them, I know the other one. I don't need to write negative. The formula has plus or minus in it. That correlates to those two z-scores. Does that make sense? Because I want to go up and down. The plus or minus is already built in. I just need the freaking number. So I just care about the 2.05. So z is 2.0. Now, why does that make sense? Can somebody help me out real quick? If you look at the little baby chart, what was the z-score for 95% confidence?
1.96. If I go out 1.96 steps up and down, I catch 95%. Doesn't it make sense then if I want to catch 96%, I go up and down a little more, right? If I go up and down 1.96, I catch 95%. If I want 96%, up and down just a little more, 2.05 makes sense. It's a little more than 1.96. Does that make physical sense? Okay. If it doesn't, it's okay. You can tell me. That's part of my job is to handle it if it doesn't make sense. Yeah.
So why doesn't that work the same way as 0.95 would, where it's in the middle of two z-scores?
It's
Since
exactly.
It's not exactly 0.02. It's
Oh.
0.0202.
Sure, but it's not right between. What's the next one next to that? On the other side. 0.01.
0.0197.
Okay, so is one of them closer? Yes.
Like a smidget, yeah.
Beautiful. So if you wanted to get the one right in the between, I would accept that because it's almost right between. Otherwise, you just take the one that's closer. Yeah. Okay. Okay. So now I've got everything I need. Yes.
Well, what's that 0.76 z-score thing, like the little chart underneath the eye, the one that we just made? The
Where are
normal-
we at? Sorry.
The normal curve on the right side, your pen tip is touching. What is that?
Here?
Yeah. Is that
This
just
is
a
a
demonstration?
9. It was just,
Oh, is it, okay.
it was just me. Yeah, if you look up 0.96, you're not going to get the right z-score because you're going to get the z-score that has
I thought
96.
it said
totally
0.76,
Yeah.
sorry.
That's all right. Yeah, no Fallout reference. Okay.
So you have 2.5. That's what I look at right here, and then under the 5.
Well, no. I don't know ahead of time what the answer's going to be. So I 0.02. Is that cool? Or 0.98 if you go below this guy, right? So if I look up 0.02, the closest I can get to 0.02 is right there. Now Teddy has a very good point she made, which was, well, 0.0197 is almost equidistant. So you could split the difference and make it negative 2.055 if you wanted to. But officially that one's closer, so we can call it 2.05. Yeah.
Thank you.
All right, now it's plug and shove. All right, do we know p hat?
0.704.
7.4, give or take 2.05 of these. So now it's just a question of, can you put it in the calculator correctly?
0.667 and 0.741.
Charles, hold on. Yeah. Let everybody else try. So first I want to know what the error is. So one of the biggest mistakes I see, it kind of sucks if you have one of the older calculators that don't do what I'm about to do. Do you see how the square root symbol is growing? I think most of you have that, right? When you put a square root in, does it grow?
Yeah.
Well, don't say it like that, because some people don't have that. So divided by 652. So there's the error, right? Now real quick, if yours instead looks like this when you do it, 2.05 times the square root, now that sucks. Do you have one that looks like that? Now, I'm not saying it sucks like, ooh, it's bad, look at you with the back up. I'm just saying it kind of sucks, because now if you cannot close that parenthesis until you get everything in, the minute you close it, you're outside of the square root. So yeah, so now you gotta be real careful. I would just not use any parentheses until I get all the stuff in, close it there. Same answer. Yeah. Okay. You guys good?
Yeah.
So real quick, if it does look like this for you, you might have one of the newer calculators. If you hit mode, if at the top it says math, print, or classic, you can change to math print. If you don't have math, print, or classic, you're stuck with classic. I'm sorry, right? So
So I can change back to math print, and then my square root symbol just grows. Okay, so that, what did we just calculate? What is that? There, I love it. That's how much I think I'm off by. 0.0366. And now I just have to subtract that. So in the calculator, I would do this. I think I showed you this last time. You remember, you don't have to do this. Just to let you know, you can hit store X. So now I can do 0.704 minus X, 0.704 plus X, because now I stored that error in the X spot.
Where's the store button?
Right there, right above all. Okay. So now I've got my confidence interval goes from good lord, it's so much glare, 667 to 0.741. All right, so how do I write this conclusion? You guys remember?
We are 96%.
We are, 96% confident that what?
With the interval.
The interval. Now I always want units for percentage problems, just make these into percentages. And then the percentage will be your units, right? The interval 66.7% to 74.1% does what? Captures or contains, I like it. The true, be careful, true what now? No, percentage or proportion, I love it. Of people that voted. So when you go to write your conclusion, you can just a smidge of plagiarism, right? You go back, you can just copy right from the question, right? If you want to. Another name for proportion is percentage, right? Most humans say percentage, not proportion.
So it's not true mean percentage.
Say what?
It's not true mean percentage.
Hell no.
Okay.
Okay. A lot. Okay. That's like saying that my car is a Hyundai BMW. So we don't have the right dance to fuse those. Okay. Fusion. Now, little bit of algebra. Everybody's favorite. A little bit of algebra. I'm not going to make you go through this whole thing, but the error in this equation is right there, right? That's the give or take, that's the error.
You want us to write this down?
Huh?
Are we writing this down?
You can just watch. I'm going to show you where this formula comes from. So it's exactly what we did last time, except it's just a little more gross. I want to solve this for n. Why is this a little more gross than before?
Bigger number.
Huh?
Because it's bigger?
There's more going on, I guess, right? Plus there's a square root there, right? All this kind of stuff going on. So what I could do first is square both sides. Is that cool?
Mhm.
That just kills the square root. Is that all right? And then, one of the best things to come out of algebra is not necessarily this fact. 10 divided by 5 is 2. That's crazy. What's 10 divided by 2? 5.
Fine.
See how these just switch places?
Oh, cool.
Because of course they do. 10 divided by one chunk is the other chunk. Whichever chunk you divide by. So what does that translate into for me, Jeff? Well, that means I could just switch n and e squared. Switch. So that's the formula there. Okay, so read through part A there, and I want you to tell me, well, I pretty much give you a hint. Can anyone tell me what the error is? What I want the error to be? 3%. Would I put a 3 in there for E? Hell no, because what's 3%? 0.03, right? So whenever we're doing math to a number, it better be a number. Percentages are stuff that we made up.
We made everything up, but it's okay. So E is 0.03. What's Z? How do I tell what Z is?
They're looking for
How confident do we want to be?
99%.
Yeah. So, can you look at the little baby chart? 98% confidence, 2.575, kick ass. So what are we still missing to be able to use this formula?
P and Q.
P and Q, I love it. P hat, Q hat. So real quick, this is gonna come up again very quickly. Let me see if you guys are cool with this. Before I've taken any sample, I have no idea what P hat and Q hat are, right? Because they are sample percentages, correct? So I haven't taken a sample yet. How the shit would I know what they are? So you can look at it two different ways. Can anybody give me a guess as to the percentage of, how do I say it? Yeah, in the Child Development Center, what's the percentage of kids who are more than 3 foot tall? 4%? What's your best guess? Do you have any idea?
80.2.
If you have some idea, I guess. But if you have no idea, what's your best guess? If you have zero idea, what percentage of stars rotate at a certain speed? Do you have any idea? So what's your best guess?
50.
50%, right? When you have no freaking clue, your best guess is 50%,
Oh.
right?
Nice.
When you have zero clue, right? It could be anything, your best guess is 50. All right, that's one way to look at this. So if you don't know what P hat and Q hat are, you just guess they're both 50%. Now here's the more important way to look at this. If there's something I don't know in my equation, should my results, let me see if I can say this correctly, should I be penalized for that somehow? If I'm trying to use an equation that requires something for me and there's a part of it I don't know, should I be penalized for that somehow? What do you guys think? No, all right, you guys are very kind-hearted, I appreciate that. I think you're worried that I'm gonna go flog myself there, but if there's a part of this I don't know, so this is all about figuring out how big of a sample I should take, right? This is about figuring out how big of a sample I should take, yes?
Yeah.
That's the entire purpose of that formula. How big of a sample do I need to take? If there's a part of it that I don't know anything about, should my sample be as big as it could be to cover for that fact that I don't know something? I should be forced to take a bigger sample because there's something I don't know. Does that make sense? That's what I mean by penalize. You guys kind of with me? Making P hat and Q hat 0.5 each makes N the biggest it could be. Mathematically. If I make P hat and Q hat both 0.5, N comes out the biggest it possibly could. So you could look at it one of two ways. Either the best guess is 50-50 when you don't know, or putting 0.5 in for each makes N the biggest it could be.
Okay.
So for part A, we have no idea. So I'm going to assume P hat and Q hat are 0.5. Okay. So go ahead and throw that in the old calculator. Who thinks they got that?
51.802.
No. Yeah. So the same thing here, I'm gonna round it up always, no matter what this decimal piece is, round it up, 1842. So I would need, if I want to take a sample and get within 3%, I have to take a sample size of 1,842. So this is one reason why we call this a feasibility study. That might not be feasible, depending on what kind of resource, what kind of time we got. Maybe I was hoping it would be more like 50, and I'm like, 1,800, holy shit. So then we just sort of let go of getting an error that good. Does that make sense?
How are you
It's
sure
gotta
that
be-
the population is even that large?
Oh, that would be another concern. Well, the great thing is, if the population is like less than that, then you just take the entire population. Then you're not uncertain about shit, right? So this is kind of assuming the population is pretty damn big, so we can't just take the entire population. I like it. If my population is relatively small, I'm just gonna work with my population so that I don't have any uncertainty about anything. Okay. Now, by the way, does what I just said make sense?
Yeah.
The only reason there's confidence intervals and all this kind of business is because we're working with samples. And a sample is almost definitely not the same as the population, right? So I've got this built-in uncertainty, I've got built-in error. So the idea about error is we didn't make a mistake, it's just the way it is. Any sample is gonna be off. So I could do every math part of this perfectly and still have an error. Because it's just the way, and that's why I love statistics. It's the most honest mathematics. Right? It's like, that's life. You can't ever know everything, so you're gonna be off by plus or minus something. Okay, so part B. Have you guys ever heard the phrase preliminary study?
Yeah.
So one reason they do preliminary studies, one very, very, very basic reason they do it is just to improve upon something like this. If you do a small study and get a little something to work with, you can then do something like this much better. So if we take a small group of 42 stat students and we find 31 of them pass the first time around, do you now know what p-hat is?
Yeah.
What is it? How do you calculate it? 31 out of 42? 738? So what's q-hat?
1 minus.
Or 262? I like it. So again, it's gotta be at least 3 places, so you can go 4 places. That's good, yeah. And now I'm gonna do the same formula, except now I don't have to assume 50-50. I know what p-hat and q-hat are. So now it's gonna be the exact same stuff, except this is gonna be 738 and 262. So in the homework, when the question says, how many people, how large of a sample, how many dogs, how many this, it's almost definitely gonna be the formula that's solved for n. And then it's which one? Well, am I talking about means? That's gonna be the z sigma over e, or am I talking about percentage? That's gonna be this.
1424.52.
Sounds about right, so then I would round up, is that right, guys? Sounds about right. 1420, that sounds good, okay. Now, real quick, 1,800 is a lot, 1,400 is still a lot, but isn't that 420 less, just about? 420, so that's about 420 less, that's pretty good. That's pretty good, we just chopped off the need for 400 just by talking to 42 people. I cut my sample size needed by 400. That's pretty damn good. Now, real quick, if you put that as the answer, I'm not gonna take points off, but what's the question exactly? How many more? How many did I already talk to? 42, how many do I need? So just subtract to see how many more I need, right? So if you stop here, I'm not gonna be all like, you missed that. It's not that big of a deal, but to really answer the question, you would just subtract the 42 that you already talked to. You already got those in the bag, right? So then you just subtract 42 to see how many more you need. What is that, 1383?
Yeah.
Very good.
Where did you get the 42 from?
From here, we already talked to 42 people.
So if I already talked to some, and now I know how many total I need, I can just subtract to see how many more I need, all right? Okay. Maybe. So let's do this. Let's do another problem like this. Then we're gonna talk about section A2, and then we'll be done for today. We'll get this out. You guys all got this? Anybody still need to see this? You good? Good, 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 okay. Okay. So let's see, I'm gonna make up a problem here real quick, so we, look at, 45 dogs. And find a mean, no, Jeff. I almost forgot what kind of problem I'm trying to find, 28 of them have a, what do you call it? The little microchip, you know what I'm talking about? You guys have it in? You can put a little microchip in your dog, and it'll be like, if they get out, they can just scan it, find you. Huh?
AirTags.
In the dog?
What's that?
In the dog?
Do I have a dog?
No, in the dog?
Yeah,
Yes.
to track it.
Just right under the skin, some through,
Oh.
so yeah. So if they get lost, they can scan it, they know exactly who it belongs to, because the collar can come off, right, with the little tag? Okay, anyway. That's all side of, I don't know where this came from, it's the first thing that came to mind. Find the 98, no, it's 95% confidence interval for the true percentage,
What does CI stand for?
huh?
What does the CI stand for again?
Confidence interval, for the true percentage of dogs with microchips. So no, they did not come from a vaccine, stop it. Dogs are not magnetic or anything, they're fine.
You said confidence interval?
So I'm gonna say CI from now on for confidence interval, because the less I write, the better it is for everybody. Yes, that's the right response is yes, Jeff. So, the immediate thing you guys should do is, am I talking about a mean or a percentage? So then you know exactly which formula to use to create confidence interval. Real quick, we got a couple of confidence interval formulas now, right? X bar plus or minus Z, blah, 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 P hat plus or minus Z, blah, blah, blah. They have plus or minuses in them. So when I do it, I construct an interval, correct? I use those if I ask you for an interval, and I do not use those if I don't ask you for an interval. Does that make sense? So I always have people trying to use those equations in the wrong place. Only use them when I ask you to make an interval, plus or minus, right? Okay. So what can you kind of gather from what I've told you? What's the first thing you notice? What can I kind of get? That I
N.
Yeah, N, what's N?
45.
45. Somebody else tell me something else. P hat, how would you get that? 28 divided by 45. All right, so do that real quick. 622?
Yeah.
Yeah, you just round it. So the next number's a 2, so this just stays 2. Yeah, and again, you could give more decimals if you want to. It's got to be at least 3. Yeah. So then what's Q hat? 7, 8. Is that cool?
be 0.377777, right? So 0.378, if you're round. Okay. What about the z-score? Actually, before the z-score, why am I allowed to use the z-score? Why am I allowed to look this up on the chart? Huh? No. It wants me to construct one. Why am I allowed to make one?
Because normal distribution.
How do I know that?
Because it's
Is N greater than 30 good?
Yes.
yeah.
No.
Is this am I making a confidence interval for a mean?
Oh, it's
I'm making it for percentage. So what better show up in my check? Percentages. Yeah. So NP hat. What's NP hat? It's 28.
28.
Yeah, but if you do it, you'll actually get what? What's 45 times 0.622? You're gonna get like 27 point something.
27.9.
Of course, because that's rounded down. But isn't that basically 28? And of course it is, because n times p equals x, right? Or just multiply the p. You're good, you're good.
So either way you do it, you get like about 28. That's at least 5. What about NQ hat?
What do you get when you get 45 times 0.378?
So roughly 17, and that is also at least 5.
What does all that business mean in blue over there? Normal enough, kick ass. Normal enough to do what? To use the chart to look up the z-score I need. So if it was not, if one of those was less than 5, we're screwed. Stats 1, we couldn't do shit. Stats 2, we could do some shit, but we just don't teach stats 2 here. Damn. Okay. Can you guys look up the z-score? Don't say it. Don't say it. Look up the appropriate z-score. Don't say it.
What do you mean by less than 5? Oh, greater than.
So if either one of them were less than 5, we could not do this problem.
Word.
Yeah.
I'll take your word for it.
Well, don't do that. Never just take my word for anything. I know what the shit I'm talking about, but never just take my word for anything. All right, you guys tell me, what'd you get for Z?
1.96.
1.96 gigahertz. So hopefully, eventually, some of these are gonna start just getting stuck in your head. You're gonna remember some of these. So now I've got everything I need to throw it into the formula. So go ahead and do that. I'll just wait.
Are you just gonna give us all the Z's on our scrap paper
What do you mean?
on the exam?
You're gonna have the z-score chart.
Well, we'll just have the Z's automatically for 90%, 5%. CI.
No and yes.
Oh, thank you.
You're welcome. So you gotta wait. As soon as I get to where we're going, you'll see what I mean. So this will be 0.622, give or take. We'll say 1.96 times this business. What was it? There you go. 45. What do you guys get for they make it the area?
0.1417.
Is that what you guys got?
Yeah.
1417?
0.5183 and 0.76.
Yeah, so now you just add it, subtract it.
I'm confused.
What's up, where?
Okay, how did you get the 1.96 on the z-score?
Oh,
Like,
alright.
when you looked up on the chart, what did you look up?
So, right now, if I give you 90, 95, or 99%, everybody should be able to get that stupid fast, right? Really crazy fast, because those are right there.
Oh, I was looking at the bottom part, not the, okay, never mind.
Oh, okay.
I was
Well, yeah,
looking
no,
at
that's
that
where
word.
they came from 95%, yeah.
Okay.
Okay. So I'm sorry, what was that again? 0.5,
183,
183?
0.7637.
And then can you write the conclusion? Go for it.
That's point, wait,
I don't know.
0.5183? I got 0.4803.
Or, yeah, it makes more sense. I am crowdsourcing.
I don't know if you guys realize that I don't have a calculator in my hand, so I've crowdsourced this. You're good.
What are we doing? What
The
you ask us to do?
conclusion, right, the conclusion. We are
95% confident
95% confident.
that the interval blah, blah, blah.
At the interval, blah, blah, blah. Oh,
Contains the
Interval.
20% of
48.03% to
76.37%.
76.37% contains true percent of dogs that are microchipped.
Now, is that a very good interval? What do you guys think? Is that a very tight interval? Is that
No, it's broad.
pretty big, right? It's pretty, why is that not unexpected? Did we take a very big sample? No, so there's gonna be inherent uncertainty to a bigger degree because their sample's so damn small. So this being this wide makes sense. Yeah, bye-bye. Okay. Okay. So, last new idea for today. And it's built off of, let me ask you this. Anybody in here ever heard of or ever drink Guinness?
Yes.
You guys know Guinness?
Yes.
Okay. In grad school, one of my professors would go to the bar after class, get some Guinness. I would follow, because he liked to talk when he got drunk, and sometimes he said what he was gonna do the next day on the test. So I'm like, oh, really? So, but that's not a suggestion. So the connection this has to Guinness is the guy who created what we're about to do. So here's the idea. The formula we have right now for finding a confidence interval for a sample mean, for a mean, involves sigma, right? In reality, so remember the thing we talked about with the spiders and whatever. So in reality, if I happen upon a completely new phenomenon, I don't know shit about it. So in reality, most of the time, we're also not going to know what the hell that is. What do I use instead of sigma? If I don't know sigma, what's the next best thing to use? S. Because I can take a sample and get S. You with me? But if it's a new species of spider, do you think you could possibly weigh every spider in that species? No, never. I could never be certain, right? Never could I be certain I got all of them. So I'm going to live with the sample. I'm going to just accept that I have to use S. Now, real quick. Remember what happened to our number required when I didn't know P hat and Q hat? There was something in my equation that I didn't know. I had to make things so that the result got bigger, correct? If I'm constructing a confidence interval, and there's a part of my formula that I don't know for certain, would my interval have to get bigger or smaller to cover me for that?
Smaller.
If there was, so if I'm constructing an interval, and the whole idea of an interval is to catch a certain percentage of data to be that sure I caught something, correct? But there's a piece of my equation, in this case, the standard deviation, we're not sure about. If I use S instead, does that equal sigma?
No.
And again, I don't know if any of you guys are listening to me and saying, I don't know what you just said, Jeff. But if I take something from a sample, how certain are you that that's going to equal The same thing from the population. I feel pretty damn confident they are not gonna be equal, correct? If I took a sample of Grossman students and took their average age, do you think it's gonna equal the average age of all Grossman students? No, I'm gonna put a ton of money on that being not equal to each other, correct? Because I'm definitely gonna make some money on that. Me gambling is big, because I'm a teacher, so. Okay, you guys kinda with me, yes?
That S that you're saying is the sum of x squared p of x.
No, stop it. What's S? What's sigma?
It's the standard deviation.
Of
Of the sample.
population. So guys, remember Greek letters, population. This is huge. Sigma is the population standard deviation. What's S?
The sample.
Sample, right? What's mu? What's mu? Population mean, it's Greek. Population mean, what's X bar?
Sample.
Greek, population, our letter sample. What's sigma? Population standard deviation. What's S? Sample standard deviation. Yes? Okay.
You said x bar is population? Or is it the other way around?
Greek letter, population. At least for that, right? So mu is the population mean, X bar is the sample mean.
Oh.
Yeah. We have to know that right now. We have to. So here's the idea. Okay. And I'm gonna come back to the Guinness thing in a minute. If I don't know sigma and I use S instead, I am almost 100% certain that I am wrong. Because S is almost definitely not equal to sigma. Are you with me? Does that by itself make sense? If I calculate something for a sample, it is almost definitely not going to be the same thing as if I had the whole population. Is that all right? Okay. So that's what's happening here. I need to do something to account for the fact that I'm trying to use something that is almost definitely wrong. So if I do that, shouldn't I have to make my confidence interval a little bigger?
Yeah.
And I love what I'm about to say, and I don't know, because I love this idea. I have to make it bigger to cover my ass, because I don't know something. There's something in the creation of this thing that I'm not sure about. So of course I'm gonna have to make it a little bigger. I'm gonna catch a little more data to cover for the fact that there's something I don't know in this equation, right? Okay, so I'm not gonna use a z-score. I'm gonna use something that will always be a little bigger than the z-score would be. Let me let that sink in. I want the confidence interval, it has to get a little bigger to cover my ass for the fact that I don't have the right standard deviation. Does that sentence by itself make sense? I'm trying to construct a formula that wants this, and I have to use the second hand. No offense, little s dude. I have to use the thing that's almost definitely not what sigma is. Are you with me? Therefore, I'm gonna have to have my intervals gotta get a little bigger to cover my ass for that, right? I don't know what the real standard deviation is, so that's kind of like the penalization. That's like the penalty for not knowing that. So I'm gonna have to use something here that will always be at least a little bigger than Z would have been to push the confidence interval out wider. And what this is called, this is called a t-score. So not surprisingly, and I did nothing to blunt this.
You said
so
T?
Here's the t-score chart. Almost like I really, really want y'all to hate me. Here you go.
Was the population x before, was that the sum of x p of x?
What?
Remember that row of x p of x?
Sure, yes.
And then we got the mean from adding that.
Totally, yeah.
Is that kind of like what x is?
No, that's the mean, it's mu.
Oh.
Yeah, S would just be the spread for a data in a sample. That's it, that's all S is.
Spread for data in the sample.
Yeah. All right. So no matter how you feel about these things, this kind of problem inherently must be easy. And what do I mean by that? I don't mean that you should have no problem with it, because you're all new to it. But they have to just tell me. They have to just tell me X bar. They have to just tell me sigma. They just have to tell me what n is. The only thing I really normally have to find for myself is z based on how confident they want me to be. And then it's just plug and chug, right? And then you have to write the interpretation, I understand, but still, the actual math work, very straightforward, right? All this does, we're gonna talk about this in a minute, right? Remember when I first gave you that z-score chart? You all feel infinitely more comfortable using it now than you did that first day. You just do, right? So I know you did not want. By the way, just to let you know, there's one more chart coming past this semester. Just one more, right? It's just the way it is. Does anything on this, let me ask this way. Do you guys notice anything on this sheet that's familiar or that you don't know what it is or anything?
It's not blue.
Huh?
Not the blue.
It's blue.
Yeah.
Okay.
That's familiar blue.
What are
Good.
degrees of freedom?
Degrees of freedom. Huh?
What is that?
Didn't we talk about degrees of freedom before?
No.
We did. So when we did standard deviation back in chapter 2, remember how I divided by n minus 1 instead of n?
Ah.
And I said, what if you had 3 numbers that average to be 10? Couldn't we just make 2 of them totally up, as long as the third one made it add up to be 30? Do you remember that?
Yeah.
Let me say this again, guys. If I have 3 numbers that average to be 10,
Yeah.
do you know what any of them are?
No.
You don't have a freaking clue. Nah. But what do you know they add up to be? What's the only way 3 numbers can average to be 10 is if they add up to be 30. Because to average them, I divide the sum by 3. So if they average to be 10, they have to add to be 30.
Okay.
Is that okay?
Yeah.
Yeah.
So how many of them can you just totally freaking make up before you got to get serious?
2.
You can totally make 2 of them up. You can make this 1 billion. And you can make this 3 billion. As long as this is negative 2 billion, blah, 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 to make the sum come out to be 30, right? So how much freedom do you have? Do you have 3 degrees of freedom? No. How much are we totally free to make up? 2.
Oh.
So degrees of freedom is n minus 1. That is why the standard deviation in chapter 2 for samples was divided by n minus 1 instead of n. Does that sound at all familiar? Anybody
Yeah.
remember? The standard deviation for a sample, it was n minus 1. That was an adjustment because it was poor little sample.
Oh, I can't write on this, right? 'Cause it's gonna-
Yeah, be careful. Just like the z-score chart, you don't want to put notes or anything on these t-score charts. You're going to be using them on tests and quizzes. Okay, is everybody with that? So if my, sorry, go ahead.
You said the degree of freedom is what?
N minus 1.
Oh.
N minus 1. So if my sample size was 11, where am I looking at under the degrees of freedom?
10.
10. Okay. That's the first thing. All right.
And there's no negatives.
Tell me this. For a 95% confidence interval, who remembers what the z-score is for that? We did one of those earlier.
1
1.96, right? Go with me now. Because I'm going to explain. Look at the 2 top rows. Anybody concerned about the tails thing? If I were you, I'd be concerned. When I make a confidence interval, right? When I make a confidence interval, how many tails do I make? So what I mean is this. If I ask you to draw a 95% confidence interval, how do you do it? You shout, right? How many tails did you just make? 2.
2.
So let me introduce a new symbol. So here's what's really cool. Can anybody tell me the total area in the 2 tails? 5%, right? Oops, let me not use, would be 5% or 0.05. Is that cool? Old news, right? 0.05. So here's what's really cool. So the symbol that means the area in the tails is the Greek letter A, which also happens to look like a fish, which has a frickin' tail. That's just too good. Area in the tails is the symbol that is the Greek letter A for area, and it has a freaking tail, right? So it's alpha. So I would say alpha is 0.05. Now what area is there in one tail?
Alpha divided by 2.
Good, alpha divided by 2, in this case it would be 0.025, are you with me? You with me? So if I wanted a 95% confidence interval, what area is in two tails? What did we just say? 95% confidence interval, what area is in two tails? 0.05. What area is in one tail? Do you see how either way you look at it, you're in the same column? Okay. So, what if I wanted, no, real quick. Jeff, don't forget where you're going with this. And this guy's just looking the total wrong way. Poor little camera. Remind me, 95% confidence, what was the z-score? 1.96. What's at the very bottom of this crazy ass t-score chart I just gave you? What's it say?
1.96.
What's it say? Large. Okay. The larger my sample gets, the more I trust what I calculate from it. Does that make sense? If I take a very small sample, do I trust its mean to be the same as the population mean? No. If I take a big ass sample, which is another name for large, the technical name for large is big ass. If I take a big ass sample, I'm gonna trust it really well. So look, aren't these bottom ones, don't they look familiar? 1.645, 1.96. This one's a little off because it's a little more precise, to be honest, but we've seen a 99% is 2.575. This is 2.576, right? So, going back real quick, because I said I would. The guy who worked at Guinness Brewery, his name was William Gossett. He was doing research on a situation where he didn't know the standard deviation of the population. So he constructed this chart, this distribution, the T distribution.
The beer dude?
The beer dude. And he did not submit his name with his research because then the Guinness Brewery would have owned that research. So he submitted it under a pseudonym. He called himself Student. So you'll see this referenced as the student's T distribution. Do you have to remember any of that? No. Okay, so you know the history lesson. The purpose of a T-score is it is used when I don't know the population standard deviation to cover my ass for that fact. If I have a really freaking huge sample, I feel pretty good that that standard deviation is going to be close to the actual standard deviation. So I don't need the T-score's help. Now look what happens as my sample gets smaller. The T-score starts covering my ass a little bit, right? It goes out a little further. I'm less and less certain. So it's going to go out a little further, cover my ass. And when I get a really stupid small sample, look at that sucker. Right? It's going to cover my ass big time because I know so little up here. How big is my sample here? 2, right? That's degrees of freedom. So the smaller my sample, the more help I need from a T-score. It's going to push my confidence interval out further. The bigger my sample gets, the less I need a T-score's help. So one thing I want you to understand right now, if I need a Z-score, I can use this chart because they live down here, right? I don't know if you guys remember, we did a 98% confidence and it was 233. Which column do I look at for 98% confidence? 98% confidence, what is alpha? For 98% confidence, what's alpha? 0.02. Which column is that? Second column. What's at the bottom of that column? 2.33, 2.326, right? Which rounds to 2.33. That's the Z-score we found for a 98% confidence interval. Okay, maybe. So, what do I got for you? I got this. This is a little worksheet, not another chart, don't freak out. I'll turn the light up in a minute. You.
ahead and try to do the first 3 problems on this sheet.
One A, one B, one C, or you mean?
1A, 1B, 1C, yes.
What's DS?
Degrees of
Degrees
freedom.
of freedom.
Um,
Degrees of freedom. You guys can work together if you want to. Alright. Let me catch up to you guys. So in part A, what's the degrees of freedom?
5.
Good. N minus 1. What's alpha for part A?
.00.
0.01, right? So which column am I looking at? First one? And I'm gonna stop at 5.
Fine.
So basically, here's something. If I look at this t-score chart and I stop, I get a t-score. If I go all the way down, I get a z-score. That's how this sucker works. I pointed that out earlier. Aren't these z-scores at the bottom? Why does that make sense? A t-score covers my ass for when I use S and I don't know if it's really close to sigma. The bigger my sample is, the better I feel that my S is close to sigma. So when it's really large, and I love that word, why do they use large? Why don't they say 3,500? Because it depends on how precise you need to be. They're like, whatever large means to you, right? So what do we get? We get
4.032.
4.032, I like it. So what about part B? Degrees of freedom would be 100. What's alpha?
0.05.
0.1. So 0.1 and 2 tails. And I stop at 100,
1.66.
right? What was 100? There we go. Yeah, 1.66. How do you mean? Sorry. So, yeah, mathematically 0 doesn't do anything to us, so. Oh, it is, but this is just 0. So if I don't write it, it's the same number. Yeah. Now here, what happens here? You guys notice something weird here?
92, there's no 92.
No 92. So just like always, if there's something I'm not sure about, I must be penalized for that.
You gotta go up.
Yeah, up on the chart, down number-wise. So I should go to the next degree of freedom below this, which is 90, right?
Yeah.
So the 90, and then what's my alpha, sorry? 0.02, so I'm gonna look at 0.02, 2 tails, go down to 90, and we get 2.368, thanks. Okay.
Why would you go down to 90? Would you go up?
So again, if there's something you're not sure about, your confidence interval should have to get a little bigger. So if I go down to 90, my t-score is bigger, which is gonna push my confidence interval out. Yeah. You like it? All right. Now,
Professor, I thought that the z-score increased when your confidence went up, right?
In order to be more confident, if everything is equal, and I just want to be more confident, then I must go further out, right?
But if you go further out, doesn't mean you're confident.
If I have a set level of confidence I want,
Uh-huh.
and there's something I'm not sure about, I've got to go further out to cover my ass for that.
Okay.
Do you see the difference? If I want to be more confident, I go out to catch more data. If I want to be the same level of confidence, but there's a piece of my equation that I don't know, I'm not sure about, I've got to go a little further up to cover myself for that.
okay. So, a t-score is basically the z-score distribution, kind of, guys.
T-score distribution is basically the Z-score distributions are sort of pushed out of it. So what do I need to know before I can use a Z-score chart, for example? I need to know it's normal. Same thing for T-scores. So, could somebody remind me why T-scores were invented?
We don't have
Because
to-
it's a new thing.
No.
What's it called, seasonal?
Yeah, they were invented to cover my ass when I don't know the real population standard deviation, right? That's why they were invented. In order to use Z or T, I need a normal distribution. How do I tell which one to use is which standard deviation do I know? So I have way too many people that will tell me, well, we know the standard deviation, so then we can use Z-scores. That makes no sense. Which standard deviation, right? Is it a population one or is it a sample one? If I only know the sample standard deviation, what do I have to use? T-scores. If I know the population